How's everyone this late morning? Good? Yeah, okay, great. So I'm Jackie Kazil, and this is Masad. We're both from George Mason University. David is a full-time PhD student. And do you want to share anything about your background?
I've been doing agent-based model. Sorry, can everybody hear me? I need to stand closer to the microphone. Cool. I've been doing agent-based modeling for a few years in grad school, in sort of government-adjacent industry for a little while, and but as a jockey.
Yeah. So most of mine has been in the graduate school program, but I come from a Python programming background. I have to make this next disclaimer. While I work professionally for the U.S. government, I am not currently representing the U.S. government today, and the opinions or anything that I say is my own and no one else's. Today we're going to talk about Mesa, which is an agent-based modeling library that we and a couple of others have contributed to, and it's based in Python. Quick question. How many people here have done agent-based modeling before? Okay, good. And how many people are familiar with agent-based modeling but haven't done it? Okay, good. So a little bit at the beginning is going to be sort of an overview of sort of different models for those who aren't familiar, and then we're going to show you how to build a basic model using Mesa and what it can do. So agent-based modeling is basically a computer simulation that consists of agents interacting with one another in order to study an overall system. Other terms that have been used, but not necessarily equivalent, are multi-agent systems, multi-agent models, game theory, cellular automata, microsimulation, individual-based simulations, and complex simulations, and I'm sure there's a bunch of others that I missed. So the first one we want to tell you about today is Conway's Game of Life. This is sort of the most basic simulation. Cells live or die based on the number of cells around them. The shapes themselves, the shapes that you see or the patterns that are created are not the agents, but the individual cells are. The one that we're going to do a lot of talking about today and show the example in is Schelling's segregation model. So in 1971, Schelling proposed that segregated blocks can arise not just by active racism, but due to mild preference for neighbors of the sameness. So you are like me in this case, the hashtags versus the little circles. And some of you might be familiar with the parable of polygons. It's a great JavaScript version of this online with little happy and smiley and sad polygons. So growing up in like the sort of detail of complexity, this is a model built in another modeling framework called NetLogo. It's the predator-prey. It shows predator-prey dynamics. There are sheep and wolves. Sheep eat grass, wolves eat sheep, and they both reproduce. Next, we have political dynamics. This was built in Repast, and for those of you who don't know Repast, it's built in Java with its own custom IDE, and agents are groups of people or sort of states.
Yeah, the agents here. So the idea here is the agents don't have to be individual people or wolves or sheep. In this case, the agents are these entire sort of simulated states that are fighting with each other and making alliances.
Yeah, and interacting. So next is a simulation on migration behavior for displaced people in East Africa. This is built in Mason, which is also Java-based, and came out of George Mason University, where we both go. We didn't like that. Well, I don't like it. I said it. And then sort of a really like a higher level, complex one-to-one simulation from Los Alamos National Lab is a epidemiological simulation where it shows infectious disease, uses census data and clinical locations, along with road networks and the way people move. So that brings us to Mesa, which is what we're working on. We started, I think, in 2014 with very bare bones, and we had kind of always did these one-off ABMs, and we wanted to build more of a framework to build these out, sort of like your Mason or your Repast or your NetLogo. And we had sort of both used a lot of these tools and we sort of took into consideration all the problems that each of the tools had. So it's a Python package, as we said. It's open source, Apache 2 licensed, and on GitHub. So one of the big things is that it is modular. So you can mix and match components. You don't have to necessarily use the grid. It has a browser-based visualization, which was a big thing for us because none of the agent-based models out there currently have it. So we use HTML5 right now and some other JavaScript libraries, but the hope is that you can sort of plug and play your own components that you want based on the models that you build. And it has built-in tools for analysis, which includes data collection and parameter sweeps. And it's in Python. So David's now going to do a demo and a walkthrough of the shelling model built in Mesa.
Thanks, Jackie. So so one of the things that on all of these other packages we talked about, the other modeling frameworks are not in Python, which is why we sort of went and built this. And so I'm going to give you a quick walkthrough through an example shelling segregation model. So just to recap, you have these agents of different colors who live on a grid. If they have a certain number of neighbors of the same type as themselves, they're happy and stay put. If they have fewer than that, they're unhappy and want to move. So in this case, these red agents would be happy because they have at least 3 neighbors of the same color. The blue agents have each one only 1 neighbor of the same color, so they're unhappy and they're going to want to move away. And so first I'm going to run the actual model with our browser-based visualization and show you what it looks like, and then give you an idea of what the code behind that with our package looks like. So this goes back, sort of ties in with what Jake was talking about during the keynote just now about serializing visualization, sending them up to the browser, and doing visualization that way. And so it's a little bit small, but so here's what the model looks like initially, and we have a graph down here which will show how many unhappy agents, and then you just hit run, and it's going to start animating. The agents move around. This graph updates in real time. You can go and pause it. You can change the frame rate, so if you want to make it go faster, hurry the whole thing up. And so you can see on the model side, it's behaving the way, well, if you're familiar with the shelling model, it's the way you expect. If not, it might be a little bit surprising, even though these agents only have mild preference for neighbors of the same color. You get this really stark segregation that emerges. And on the modeling side, you can see that this is also the actual model is running on the back end in Python. And then the data that's generating is being piped up over a WebSocket to the browser, which is then drawing all of this using JavaScript and some pure HTML5. So you can reset it. That resets the model on the Python end. Run it again. And so the code that generates that, this code that sets up the server, just looks something like this. So for the information here on how many happy agents there are, it's just creating this text element which renders the happy parameter in the model, the happy variable. For the grid drawing, there's just one function that defines some JSON for what the agent is going to look like. So it's a circle. It's going to have this radius. It's going to be filled. It's going to be layer 0, so you can have multiple. If you have a lot of different agents, you can have different layers. And then the color is just going to be determined by the agent type. And then there's a modular server, which is already written, doesn't need to be subclass or anything, and just gets a model type, some model parameters, and an array of these visualization elements that already come prepackaged with the framework. And when you run it and launch it, it already knows how to spin up this whole visualization, create this browser window out of a template, start drawing it. The interface is already there. So the startup costs for this kind of visualization are very low, especially compared to Mason or Repast. But you don't have to use the visualization, unlike in NetLogo, where if you're familiar with it, you're sort of always in this custom framework, which always has a grid, always has the visualization running. And because it's in Python, we can also pull up the IPython notebook and run the same model in there instead. We can just import our model import basic matplotlib stuff, and create a model object, and then just run it. Just step through it 100 times unless it ends sooner. See that happening in real time. And so the data collector, which is just in the model. So this is what the model code looks like. This is all up on GitHub. And we create this data collector with just every step of the model goes through and counts the number of unhappy agents, stores it internally. And we can pull that out directly into a pandas data frame, so it already knows how to do that. As you can see here, the beginning of count of how many unhappy agents there are. You can plot that directly in your IPython notebook, or Jupyter notebook, that's what we're supposed to call it now. You can get so the data collector can also get agent level variables, so this is just every agent, X and Y, just for demonstration purposes. And then you can do experiments. So you don't need to, instead of with other tools where you need to run something, export it to a CSV, load it somewhere else, and then analyze it, you can run the experiments and analyze them directly in the notebook. So here we have some function that just goes over and counts how many agents are segregated for this example. Then give the parameter sweeper a set of parameters. So we're going to hold all of these fixed and then just vary the homophily, so how many similar agents each agent wants from 1 to 9. For every model run it for 100 steps and count what the segregation is like at the end. And after we've run all of that, pull the data out into a pandas data frame and plot that, and immediately do the batch run the experiment, see that we have this change. So this is on the x-axis here, you have the homophily. This is the segregation at the end. And if you look at this and you have a question, so why is it that when you have the high homophily, suddenly the segregation goes down? You can go back, immediately change a parameter, run the experiment again. And you can see, well, in this case, the reason is because nobody's ever satisfied. You can't get, it's very hard to get that number of neighbors. And so the reason there's no segregation is because nobody's just ever happy. And also because it's Python, it plays nice with any other Python visualization tools. So HoloViews, which we saw the other day, you can also use to visualize a model run like this. So here's just some code bringing in HoloViews, creating a holomap. And here's another visualization of the same model with a nice scrubber that can go forward and backwards in time. And I'm not entirely sure how to do this ourselves, but the HoloView people made an example for us. This is another Mesa model of a forest fire spreading, and have this nice animation that you can run, you can pause, you can scrub through it. And so this is all a Mesa model being visualized with HoloViews. There's also the sort of browser-based server visualization of it. And you can run these experiments the same way, pull out data frames. And I think that about covers it. So.
Okay. So to wrap up, future work. Thank you. Future work. So we can keep you in the suspense. Networks, this is an obvious sort of next step for us. So we've had a lot of conversations about that. Checkpoint and fixed seeds. So to be able to, I think you can explain this better, but to
yeah, so you can sort of, there's hacky ways right now. You can just set the random seed globally, and that gives you reproducible models. But we want ways to be able to build that into the model, have each run of the model store its seed. Checkpointing is being able to just serialize a model down, pause it, freeze it, and then pull it back and run it again later on.
And to be able to reproduce the models that we actually create in a consistent way for testing. More and better visualizations and visualization components. Optimization, going through to see where our slow points are, and also when we try to scale upward more, optimizing it in that way. I said scaling. Geospatial, obviously, and then whatever you guys want to contribute. We're going to be at the sprints working on this, and so if you would like to help us, we have very easy ways to get into the framework and for you to contribute. And besides that, did you want to show the activation?
No, I think we're out of time.
Okay.
But there's a bunch of other features. You can set the activation scheduler. There's a bunch of other cool features. It's all up on the GitHub repo. You can find it. You can email us. You can find us on Twitter. Thank you very much.
Plenty of time for questions?
Yeah.
Quick question. So how are you scaling the agents on the back end? How many agents do you run on your laptop?
So it depends on the complexity of the agents. The shelling model is on the order of 400. The forest fire model, which has much simpler agents, has 10,000 agents. You can run, we haven't sort of done any sort of hardcore stress testing, but it's basically, you can run as many as you can hold in memory. It just depends on how quickly you need the results. Yep.
Are you planning any parallelization?
We'd like to. That's something we neither of us, or at least I haven't worked on as much, so I need to sort of learn more about that. But ABMs are a little bit tricky to parallelize because the agents are interacting with each other. So parallelizing and running multiple sort of runs of a model separately is easy. Having a single model distributed is a little bit more tricky.
It's not that hard.
Okay, well, we should talk about it later.
Yeah.
So you mentioned shelling the Firestrike. How many other models have you developed?
We have, I think, a library of about 5 example models. We've also developed some other models just in our own sort of research and work that aren't part of the core repository. And so it's been a bunch of some spatial models, some econ models, some sort of game theoretic models.
So these are the models we currently have. And we use a lot of these sort of to test the framework and to make sure that we aren't sort of breaking things. But that's one of the easy ways to contribute or sort of dive into this is to build out a model, contribute it back, and help us make more robust.
And we've been sort of going through and trying to get some of the sort of canonical models, so like the shelling model, Flocker's demographic prisoner's dilemma, Epstein, civil unrest models, sort of working through and adding some of those.
So I'm actually from an econ background myself, and I think these are super cool. My reaction from professors in the past when I was asked about these sorts of models is I hear often like they're not that useful because you don't get an equilibrium and it's hard to sort of say something generalized. I was just wondering what sort of adoption you guys have had so far with the tool, and if you think that this model could sort of change your attitude to this kind of stuff.
Good question. I think that's a problem that anybody who works in this area or uses this methodology faces. The tool itself is fairly new. This is our first public presentation of it. I think agent-based models more broadly, it's hit or miss. Some people have a real visceral reaction against them. Some people are really into them. It really depends on the venue and how you pitch it, and we can chat about that later. Any more questions? Okay. Thanks a lot.